Okay, hello everyone. This is Ahmed Emad, and I'm a PhD student at KTH, Stockholm, Sweden. Today, at the part of RAIS Web Seminars, I'm going to take about graph representation learning in heterogeneous graphs, and it is part of the research I am doing in my PhD. We have here on the left an example of a graph that consists of nodes, which is the blue points we see, and each node, each pair of node is connected with an edge, and we call this a graph or a network, and we have this around us. Most of the data we have nowadays actually come in the shape of graphs. Examples of this online social media like Facebook, and we have friends on Facebook. So this network of friends is an example of a graph or a network. We can actually find it too in a micro level examples like protein to protein interaction networks and drugs. We can also see it in academic graphs where we have authors, papers, and venues. These are our nodes and they are connected together. So we have a lot of graph examples around us, and graph representation learning actually trying to learn a representation for each node, a meaningful representation for each node. So how it works? We try to learn this matrix you see over here, and this matrix consists of uh, n, which is the number of nodes in the graph, times d. D is the dimension that we choose for our representation. When we get this embedding, it means that for each node has a vector of length d, and the vectors themselves, sometimes we call them embedding, they should reflect the structure in the graph. So if the two nodes are connected or share similar neighbors or be in the same community, their vector should be closer than than the vectors of other nodes that are perhaps different or distant, and so on. By converting the graph to such embedding, we are able to use this embedding, this learned embedding, in a different tasks, downstream tasks. One of them is node classification, where we get node and try to classify this node, what like in the case of author, what the research field this author is working in. We have also link prediction, where we try to predict the missing edge between two nodes in the graph. We also have a community detection, where we try to cluster the graph and so on. And this cycle we have here is called a graph representation learning. Today I'm going to talk about this. I'm going to talk about three different research papers that mostly apply this concept, but in heterogeneous graphs. And heterogeneous graphs typically consist of different type of nodes, not one type, but different types of nodes. Here we have a toy example of an academic network, and we have the P. P is for paper, and A for authors. So we have different type of nodes here in this graph, and this is we call it, and of course different type of edges, because an edge between paper and paper will imply citation, but an edge between author and paper will imply authorship. So we have like this author A1 have actually authored the papers P2 and the paper P1. This is a heterogeneous graph, and I'm going to talk about hint topic. It's published in 2017. Also, I'm going to talk about HAN, or Graph Attention Network, published in 2019, and then MultiSage 2020. All of them work with heterogeneous graphs. So let's start with hint topic. We work with the same toy example, and typically, heterogeneous graphs have a lot of information, richer information than the homogeneous graphs, where we have only one type of nodes. And there is many ways in the literature to explore or to collect data or information from this graph to give them to whatever model that will try to learn the representation. One of these ways is called metapath, which is the paper Hinterbeck is actually employing. A metapath consists of different more than one edge. So set of connected edges will make one metapath. In this graph, we have two edge type BB, which is mean citation, and we have AP, which mean authorship, right? Now, if we choose to extract all the metapaths that have at most a length of two, so where they are within two hubs, then all the possible meta passes, or sometimes we'll call them relationships, from this graph will be, as you can see, BB, PA, AP, and then we have PP, which is a two hub, and this is all the combination we can extract from such a graph. Okay, so this is a meta path. So a PPP could be example of it, P1, P2, and P3. You should know that each meta path of them has a semantic meaning according to the authors. So if I have like APA, which is author paper author, it means that these two authors actually collaborating in one paper. If I have author paper venue paper author, see the relation between these two authors mean that they published papers in the same venue, and this is different than actually working on the same paper. So we can see that between the same pair of nodes, we can actually have more than a meta path, or more than a semantic relation. And this is an example of the rich information that heterogeneous graphs typically have. So what we do first, we extract in Hinterbeck, we extract all these meta paths, okay? And the objective of their model, they will try to, given a pair of nodes, they will try to predict the meta path that connect this input pair of nodes. To do that, there's two steps we'll go through in this paper. First step is to prepare the training data, which means extract all the meta paths and then put them in the right format. That's the first step. Once we have this training data, we apply the representation learning model itself to produce the embedding of the graph, the embedding we mentioned earlier. So the first step, training, how to prepare the training data. So we said, like, we decided it could be K-hub, but we decided in this example to be two hub metapath. Okay, so we set the length to be 2, and then we extract all the possible metapaths, as you can see. Once we do that, we initialize a normal random walk. In case you don't know what's random walk, you start from some node and then you randomly go in the graph. In this example, our random walk will be from P1 to P2, A1, then P3, then back to A1. And this is an example of a random walk, okay? So we have all the possible metapaths we chose, and we have an example of a random walk. And then comes a step where we're actually trying to parse this random walk given the metapaths we extracted, okay? So we start from the first node, which is P1, and then we try to see, okay, which one of these metapaths applies to P1 with its neighbors. So we have P1 and P2, which means a metapath PB, okay, and we see it here. Also, we have P1 and A1, P1 and A1, both them extracted from the metapath. So we took P1 and A1, and this is an example of PPA. This is a metapath that connects P1 and A1. So we basically go through all the metapaths, and we see which one of them applies on P1 with whatever its neighbors. And we do that, for example, for P2. For P2, we have P2 and A2, and the metapath connect them is PA, and then we have P2, P3, and then they have PAB. Okay. So if we actually check the graph, so we have P2, and so we have P2 and A1, and they are connected with the metapath PA. And then we have also, and we have P2 and P3, and they are connected with the metapath PAP. Okay. I think you also can extract P2 and P3 and put PP as an example of metapath, but here for illustration, we didn't try to extract all the possible training examples. So once we have this format for each node in the random walk, and we apply this, by the way, on all the random walks we have, we try to put them in this format. So we have X and Y, which is a pair of nodes. In this example, will be P2 and A1, and then the meta path that connects them, which is R, and then finally we have 0 or 1. 1 means that the node X and the node Y are actually connected through this meta path. 0 if an X and Y are not connected through this meta path. Okay, and we call this a negative sampling. And once we prepare all this, we call it our training data. And there is a couple of issues or challenges that I think we need to mention here. First of all, extracting the meta path, the training examples, you can run into a cycles. An example of this is A1, A1. Like we can see from this meta from the random walk above, A1 and A1. A1 and A1, and they are connected through the meta path ABA. But actually, this doesn't comply with the semantic because of this APA metapath. Because APA means that these two authors co-authored together the same paper. But in this example, actually, the two authors are one, so you cannot be co-authoring with yourself. This is a slightly different semantic. Therefore, we while extracting the training data, the authors made sure that they exclude all the cycles. Also, we apply negative sampling. So once you generate all the positive samples from the random walks and the meta passes, you try to also extract negative samples by choosing nodes that and the meta path that do not and the example of meta path that actually doesn't connect these two pair of nodes, and then we have 0 because it should be predicted as 0 that they do not have such a relation that connects them. Okay, so negative sampling is an issue or a challenge in such case because we need to actually make sure that we don't have an erroneous negative examples, which is examples that are not actually negative. Okay. So once we have our training data preparation and it's done, the second thing is the model itself. Okay. Then how we learn the representation of the nodes given this training data. And we have such a model here in Hintovik, and this is the Hintovik model. So they have X and Y, which is the two nodes, and they have R, which is the meta path that connect them. You remember these training formats, right? This is our training entry, X, Y, and R. The output will be 0 or 1. 0 is if 0 if actually X and Y are connected through this R relationship, 0 otherwise. Okay, and this is our model. So that can be formulated in this formula X. So the X times the weight Wx, Y times the weight Wy, and then R times the embedding Wr, and then all this are fit through a sigmoid, which is nonlinear, trying to predict 0 or 1. Okay. You should know that the Wx actually will, after we're done training, this Wx will represent the node embedding, okay? And Wr, we can say it will represent edge embedding, sorry, relation embedding. We can actually learn metapath or relation embedding too. But a slight modification here, we can see this f function. So Wr actually fit through an f, through a function before it gets multiplied by before it gets multiplied by the other terms. We can see this here in this formula. So we can see that R times W, and then times it goes through this function f before it gets multiplied with the others. And we only apply this on the relation embedding, not the nodes embedding. And this is a regularization. This f is a sigmoid function, which will squash the value of whatever comes from this multiplication to be between 0 and 1. And the authors believe they did that because they believe the values of the embedding value of the metapaths shouldn't be very large compared to the embeddings of X and Y, the nodes. So they squash it between 0 and 1 to squash it into a small range. Also, they put it through from 0 to 1, not from -1 to 1, in case you're asking, because they thought that they want to make the learning easier. So if X and Y nodes are actually correlated, then they should have the same sign. If they are similar, they should have the same sign. If not, then they can have a different sign. And if they allow negative values coming from R, then that could reverse the result of multiplication X and Y, which may hinder the learning in the model later on. So they put actually they made sure that the value is between 0 and 1, only positive and only small values for the relation R. Okay, so this is the model, and the learning the loss function we have here is normal cross entropy function. So L, which is 1 in this case, log the probability in case if it's 1. If it's 0, then 1 minus L. And this is their model. They trained now this model on 4 data sets, and all of them you can see they are heterogeneous data sets. So, for example, if I take DPLP as an example, it consists of 3 nodes: paper, author, and venues, and 2 different type of edges, which is authorship PA and paper venue, which is BV. And this, for example, of real life data or graphs, they applied also space lines, deep walk line not too big, as a homogeneous models, baseline models that were designed originally to work with homogeneous graph, and then they apply also these models that were designed to work on heterogeneous graphs similar to Hinterbeck, and they show actually that they have a significant better result than all the baselines. Now, there's a couple of advantage for this model for Hinterbeck. First of all, they now are able to extract different metapaths, which means different semantic, and they are able to actually employ it in a good way, regardless of the length. So we no longer work on edge; we work on the metapath, which is longer, and the model is actually flexible and is scalable um, with the way it was designed. But for me, I think there is a bit of non disadvantage, or a kind of a negative points. First, for me, the regularization, it wasn't really clear in the evaluation. I mean, they provide good interpretation and good analysis for the regularization, why it might work. But I think this regularization needs to be investigated further, at least experimentally. Also, they employ different metapaths, as we saw in the architecture, but they deal with these metapaths to be of an equal importance. But in reality, actually, some semantic or some metapaths that connect between 2 pair of nodes may be more important than other metapaths that will connect the same pair. And actually, this next work is gonna tackle this point. And this is Hinterbeck. Now, the next work is Han. It's published 2 years after Hinterbeck, and it's abbreviation for heterogeneous graph attention network. So as you can see, they are work with heterogeneous graphs, and they're gonna apply attention. Okay, and because they're applying attention, they work with a graph neural network. At this point, I'm assuming you know what's graph neural network. It's kind of similar to the method they are using here is similar to graph convolution neural network. You can actually check this before we continue this video. Okay, and they say in this paper that heterogeneous graphs have a lot of rich semantic information, and we have they add to what we said earlier about heterogeneous graphs in Hinterbeck. They also say even the nodes themselves, different type of nodes have different features. So this toy example, we have a small graph of movie. So we have actor, movie, director. This is the type nodes that we have, and we can see that actor and movie and director are connected together. So we have AMD, which is a director and author working on this movie. And also we have AMA, which is like two actors working in the same movie, right? Between actor and director, or actor and movie, we have different features. For example, actor may have age, sex, and nationality. Movie have plots and the actors, right? So nodes have different features, and features could be very useful information to consider besides the structure of the heterogeneous structure of the graph. And because nodes have a different feature, they should be represented in different feature space. Okay, so this is another example of the rich semantic information we have in heterogeneous graphs. And similarly to Hinterweg, they work with the concept of metapath. So the metapath here we have movie, actor, movie, for example, which like two movies that were casted by the same actor, and we have movie, director, movie, which is two movies that got directed by the same director. Okay, and this is an example of two metapaths that we can extract. So the first concept is metapath, which we already know. Okay, then another concept that we need to now pay attention for is called metapath-based neighbors. And metapath-based neighbors is given a node, you decide what are the neighbors of this node given a certain metapath. So, for example, here you decide that the metapath I'm going to consider is movie, actor, movie, right? And the input node will be M1. Okay, so we can see M1, A1, M2. We can see it in this graph, M1, A1, M2. And this is, so M2 is the neighbors of M1 if I work, and the same for M3, if I work with the metapath movie, actor, movie, okay? If I change the metapath, so movie, director, movie, we can see that the neighbors for M1 will be only M2, not M3. So M2 actually happened to be a neighbor for M1 either way in the two metapaths, but M3 happened to be neighbor to M1 only in a certain metapath, which is movie, actor, movie. Okay. So we call it the metapath-based neighbors. The neighbors of a node given a certain metapath. So these two notation, metapath and metapath-based neighbors, are two important notation to explore the graph for hand. Now, let's see actually how the model is working. They apply convolution neural network, graph convolution neural network, and so basically graph convolution network is about aggregation from aggregating the features and the embedding of from your neighbor nodes up to into one node that you're trying to learn its embedding. Okay. Difference here, they apply what they call a hierarchical attention. So they say actually we have two different levels that we need to apply attention to. One, which is the node level attention. The other one is a semantic level attention. Both of them make a complete hierarchical attention. Okay, the node level attention is like given a certain one meta path and a node, you only consider all the metapath-based neighbors for this node. So you only fix the metapath and work with the neighbors given node zi and metapath theta 1. Okay. And in this example here, this we call node level aggregating. So we have here zi for the metapath one, and we have zi also, but for metapath 2. So metapath, sorry, b. And these are neighbors of node I given the metapath b, and these are neighbor of node I2, but given the metapath 1. Okay. So basically, in this attention, we only focus on the metapath-based neighbors, and we learn multiple embedding for the same node given different metapaths. Okay, all the metapaths that this node is actually engaged in the graph, and we call this a node level attention. Okay, so this part is node level attention. We can see the intuition behind this. So if we have the movie node, it's the terminator, and we're trying to decide the type of the movie, and we decide that the metapath we're gonna consider will be movie, director, movie, right? And once we apply this metapath on this node on the graph, we find that we have the terminator James Cameron, Terminator 2, the terminator James Cameron Titanic, and let's say that the task is we're trying to predict the type of the movie. The Terminator should be like action, science fiction, and so on. So we have Titanic and the Terminator 2. Both of them are neighbors, are metapaths, path neighbor for Terminator. But which one of them is more relevant to predict the neighbor, the label of Terminator? Of course, you can tell that Terminator 2 is more relevant than Titanic for the Terminator. Okay, so this is an intuition behind why we need to apply attention on the neighbors, the metapath space neighbors. And this is a formula. I don't want to go through the formula right now, but basically it just this is H is the embedding of the neighbors, and they are aggregated through, we can say, as kind of an aggregated mean, and through nonlinear function, and you get the here we get theta, which is the embedding for the node zi in the metapath theta. Okay, so if we have like two metapaths or three metapaths, as you see in this drawing, we have theta 1, and we have also theta I, and we have theta b. So this is like the three embedding for node z, zi. Okay, so once we apply this for all the nodes, we call this node level attention. Then comes the next part, which is the semantic level attention, which is the part you see here. This part is focused now on, once we have different embedding for the same node given different metapaths, we want to aggregate all of them into one embedding. So this node, which is zi, will have one final embedding. But when we do this, we want to apply still attention to see this, how it works. We have the same example, Terminator, and we want to predict the type of the movie. But now we have two different metapaths. We have movie actor movie, and we have the metapath 2, which is movie production year and movie. For the first one, you can see that the Terminator 1, the Terminator 2, they were casted by the same actor, Schwarzenegger, which is basically a guy who is an actor that works mainly with action movies, right? And then we have Terminator 1984 and Birdie. I'm not sure what's the type of Birdie. I think it's like romance or something. Maybe, I'm not sure. But it's we can see this example, these metapaths give a less relevant information or a signal to decide on the type of the Terminator, right? So we have two different metapaths, and the attention here is trying to apply which metapath is more important now, not which neighbors, but which metapath. Okay, and once we apply this, we get the final Z, which is the final embedding for the node Z. And now we apply, and now we call these the hierarchical attention node level inside one metapath, and then attention across all the metapaths. And we apply, the author apply this their model on different 3 data sets, IMDb, SEM, DBLP. They use this as a homogeneous baseline. You use a couple of heterogeneous baselines too. And also they apply, because they are using convolution neural network, so they take a GCN and graph attention network. And here they apply these models work with homogeneous graphs, but they are based on convolution, so they use features as well. The other models, when they do not use convolution, so they do not use features. Okay, and then they apply also themselves Han, but with two mini variants, one with only the node level attention, one with the semantic level attention, and then Han, which is the whole hierarchical attention. Okay. And after applying the result, they show, after doing the experiment, they show that they have a better result than all the baselines. And actually, Han itself has a better result than only with one of the attentions. You need 40 attention. So the output of the conclusion that we can get from their experiment, they find that applying metapaths actually give better results. And we can see this by comparing Han and GCN, for example, or graph attention only, because once we apply attention, we significantly get Han get significantly better results. Also, the conclusion, they show that applying the structure and feature information give better performance. They know that because Han itself give better result than MetaPath, for example, which another approach that employ also MetaPath, but they do not work with teachers. Finally, we can see that attention works better because when they apply attention, they get better results than when they apply only one kind of attention and the normal average. And this is the takeaway that we can get from the experiments. And here's some visualizations that show how when we try to visualize the learned embedding for these four methods, and we can see that MetaBus, Topic, and Han is actually doing well on clustering, not mixing up the nodes, the different node types as GCN or CAP. And Han seems to be giving better results, which shows that features and attention and MetaPath, all these together, that what give Han the advantage over the baselines. Okay. Some of the good points we saw from this model, they are well designed, they work well on heterogeneous graphs. I mean, given the results, the complexity is not high because not high because the attention itself is shared between nodes and MetaPath node pairs. So the complexity is linear, and because we have attention, we are able to have a good interpretability on which MetaPath is more important than the other, so we can do a bit of a qualitative analysis. Some of the weak points we possibly weak point in Han. First of all, is a convolution pace. So we have strong results, yes, but we also assume that we have labels. Some of the nodes are labeled. So we work only with semi-supervised learning, not fully unsupervised learning like the random walk-based methods. Example of it is Hintovic, that was a random walk-based method. Also, this is not a second point. It's not like a negative point, more than an observation. In their evaluation, they only used a few number of real life data, and the data was very small, and the metapaths were very small. So I would like to see how the Han will work on bigger graphs or larger scale graphs. And by this, we now finish talking about the second study, the second research paper, and MultiSage is the third and last one we have here. MultiSage is also work with heterogeneous graphs, and you should know that they assume the graph to be a little bit different than the first two research work. They have here target nodes and they have context nodes. That's how they see it, and they are really interested in learning the embedding of only one type of nodes, which is the target node, that basically the ones that have labels, the one that you're trying to predict labels for. The other nodes, they call it context nodes. Okay, they present a context for the target nodes. So, for example, T1 and T3, both of them have T1 has C1 and C2. So basically, T1 participate in two different contexts. T3 participate in C1 and C3. So a different two contexts. Okay, and we call this actually a bipartite network. So we can say that MultiSage work with bi or multipartite network, not a complete heterogeneous graph, in the sense that there will be no age between the same type of nodes. You cannot see an age between T1 and T3, for example. So now they want to learn the embedding of T1. So you can see that the point of view that they have for this problem is they want to learn the embedding of nodes given a context. It's more of a contextualized learning or context-aware learning rather than to be learning on heterogeneous graphs like before. So to do this, first of all, they say we want to contextualize the interaction, and the interaction, it means a connection between two target nodes. So first we have how they do that. They say actually we have a node T1 which have an embedding, right? Or we're trying to learn an embedding for, and the first thing we do, we try to calculate the embedding of T1 given C1. and the embedding of T1 given C2, the two different embeddings that the T1 interact with. And they call this step is contextualizing the embedding of T1, in a sense that they project the original embedding of T1 into different subspaces according to the context. So we have multiple embedding, as many as the number of context nodes that a target node has a connection with. In this example, we have two context nodes, T1 and T2 for the node T1. So we have two possible embeddings or projected embeddings. Okay, the same for T3. How to calculate this equation T1 given C1? There is many ways to do it. We can have a element-wise multiplication. We can have a summation, or element-wise summation. Also, that can be learnable through a neural network. They tried all these in this paper. They tried all these methods, and they find that the element-wise multiplication somehow give better results experimentally. So after they do the first, so after they contextualize the node embedding, the target node's embedding, here comes the model itself, and they base their work on the graph attention network. And this is graph attention network is a paper, original paper that you may want to check first, but basically graph attention network, you have a node, a target node, which is H1, and then you have these neighbors for H1. You have neighbor from H2 to H6, and you are neighbor to yourselves too. And then you try to learn H1 prime, which is the embedding of H1 after you aggregate after H1 aggregate from itself and all its neighbors. Okay, so they do that through they learn these weights, these alpha weights, which is like you can say attention weights. Which one of these neighbors is more important than the other for H1? And once they learn this, it becomes more about like a weighted mean. So they take the embedding of H1 multiplied by its equivalent alpha, and as you can see, I don't have the formula here, but they do this and get H1. MultiSage straightforward is a straightforward extension to the graph attention network, but from working on homogeneous graph and two nodes, pair of nodes, they're working with triplet, because here you have H1, which is a target, you have H2, which is a target node too, and you have a context node that connects between them. So you can view the graph now as target nodes connected through context node. This is the only way you can work with target node and context node. So the interaction between target nodes can only happen through context nodes. And now they apply the same approach. So first of all, they apply the contextualization step that we saw before, and this contextualization step they applied for H2, for example, given C2. So they first get H2 given C2, and they get H3 given C3. You might as well have H2 connected with H1 through a C4, for example. So you will have H2 given C2, and you have H2 given C4. So it's like you have a different influence from H2 through different contexts, right? So first of all, apply the first step the last step we saw before in the previous slide, and we get the contextualized embedding for H2. And after we do this, we apply the graph attention network by learning the attentions weights alpha for the triplets, and and what and then do some kind of weighted mean. We can see the formula here. It's basically weighted mean alpha times the projected or contextualized embedding. Okay, and this is summation. Also, we have another summation here, which is D. D is just a way like how many times you want to apply the attention all over again, because they need to stabilize the connection. Stabilize the weights, the average is calculated. To do this, you apply this attention like D times of attention simultaneously, and then you average also over them. And that's how you get the final embedding of the node of a given node, which is node V. In this example, it was node H1. or H1 prime, okay? And this is the way that MultiSage work. Now, here I just trying to list the different similarities and differences between MultiSage and the first two studies. Similarities here, first, MultiSage is a graph neural network, which is working on heterogeneous graphs, which is similar to the second work, Han, but MultiSage is more of a restricted version because they have a lot of assumptions. Actually, they assume that the graph is multipartite, not a complete heterogeneous graph. So they are similar in terms that they are graph neural network, but they are different because they are multipartite, not heterogeneous graphs. Okay. MultiSage considers the feature structure and the structure and feature information of the nodes because it's a graph neural network, and this is similar to Han, but it's different than Hintobek. Okay, and they apply attention mechanism, and this is again similar to Han. So this is similarities between MultiSage and the previous course. Differences: it's a multi-partite network. Also, the way they formalize a problem is more of a contextualized representation learning because they only want to learn the embedding of the target node. They do not care about learning the embedding for the contextual node or context nodes. Uh, Also, there's a strong assumption in the sense that all the interaction should be done through context node, and two target nodes cannot be connected. And there is usually they have one dominant context node that can connect two pair of nodes. Like two pair of nodes can only be connected through one context. Two target nodes can be only connected through one dominant node, one dominant context node, and this is not very realistic. We have example here of Harry Potter movie and Lord of the Rings movie, and you can see they have context node, which is the type of the movie. In this case, is fantasy. In this case, it's an adventure. Both of them are the types for the two movies, and you can see that both of them are important. You cannot just take one of them and exclude the other. So this is the similarities and differences between MultiSage and all the other work. And here I do not, in this slide, I do not actually talk about the evaluation. It's more of an MultiSage is more of an industrial paper, so it's a bit, yeah, it's not very clear. We cannot really get much insights from the results, but you can actually check the paper for this. And yeah, now I think by this I finish my seminar, and I hope you get to learn something about this domain graph representation learning. If you have any questions, please uh, contact me. I'm gonna leave my email later on these slides when I upload them. Thank you. See you guys.